to you. Joris, the floor is yours.
Okay, thank you, Mechtold. While I'm sharing my screen, I would like to thank you and Suzanne and the rest of the team here for setting this all up and making this happen. So that's really great. And I would like to thank you all, the rest of you all, to skip the 8 o'clock news to join us here. But yeah, I guess it's the same news every day anyway. So you might as well learn a little bit about what we're trying to get underground in the south of the Netherlands. So what is that? That is Europe's next big research infrastructure, and it's called the Einstein Telescope. And there, lying on the floor, you kind of see an overview of what I'm going to talk to you about. So first, I'll let you know what gravitational waves are and what we've seen so far. Then we'll go into the successful detection methods, the large-scale interferometers, of which Einstein Telescope is the next step in that. That Einstein Telescope will then be described before zooming in on something that I'm personally working on, which is another inertial sensor. Looks a bit like the most sensitive one that I developed during the PhD, but now we're going cryogenic, so I thought I'll make some advantage of that. So let's get started. This is a representation of a visual representation of the mathematics of general relativity, the theory that made Einstein a superstar and is our best description of gravity. So what you see here in this plane, it's a sheet of lycra. Space-time is of course 4-dimensional, but if you think of it as a 2-dimensional thing, then masses will curve that space-time. So you see that this heavy thing, which could be the sun or something in the middle, curves space-time. And then if you move another mass, a smaller mass like a comet or the Earth, into that curved space-time, you see it takes an orbit. So it thinks it's going in a straight path, but actually it's following curved space-time. And that line that it traces out is called a geodesic. But this is a very static representation. You know, the sun is there doing nothing, and there's another ball rolling around there. So if we want to look more at the dynamics of general relativity, then we can, for example, have two heavy masses revolve around each other. And let's see what happens then. So you can see here that with that same lycra and a nice drill and a wooden beam and some wheels, you can make a representation of gravitational waves in the same way, in the same representation as we saw before. So these waves are traveling outward. And of course, these wheels make gravitational waves. Like if you now revolve your hands around each other, like I'm doing now, you make gravitational waves, but these are not measurable. You want to have a recipe for strong gravitational waves. So what do? You wait for signals from two black holes. Oh, yeah, here we go. So here you see two black holes revolving around each other. This was a video made after our first detection, and they smash into each other, sending out a pulse of gravitational waves. Now this pulse travels all through the universe, unimpeded by anything really. It's just stretching and squeezing space-time as it moves along, and at some point it will hit Earth. So here you see these waves coming, their frequency going up because the gravitational waves are revolving around each other's, or were revolving around each other's faster and faster, and they make the Earth wobble. Of course, that effect there was vastly exaggerated because, yeah, in 2015 and afterwards, we didn't feel anything like this. So we need to build these very, very precise interferometers, of which this is an example. This is LIGO Hanford. So this is in Washington State, in the left upper corner of the United States. And you can see two very long arms. These arms are each 4 kilometers. And inside there is something that we call the interferometer. So here you see a little video of a simplified interferometer. So you saw a laser beam being split by something we call a beam splitter. This is a bad mirror, if you will, because 50% of the light goes on, transmits, and 50% of the light is reflected in a 90-degree angle. Then you have the two end mirrors at the end of those arms, sending the light back to the beam splitter. And there's this process called interference. And we'll look at that in a bit more detail later. But for now, you have to realize that this interference decides where the photons go. So do they go back to the laser or do they go to our detector? And you can see that once a gravitational wave passes, these arms are stretched and squeezed, and you can see the blinking of light at the detector. So that's the signal that we're waiting for. So there's not one detector, but 4 now operational globally. So you can see LIGO Hanford again in the left lower corner, and another LIGO in Louisiana in the right upper corner, more in a swampy area, as you know Louisiana is. Then in the left upper corner, you see Virgo, which is in Italy near Pisa. And in the right lower corner, you see Kagra, which is in Japan. And as you can see, it's underground, or rather it's in a mountain. And yeah, I've been to both of them. I've been to both. Virgo is where I worked actually quite a lot during my PhD. And I also had some visits to Kagra. And you also see me in clean room garb, and you see behind there my wife also showing the sign which you do as you take a picture in Japan. So now a little bit more about these gravitational waves. So here you see a formula on the left, and you see it's a formula for strain. And strain is really the stretching and squeezing of space-time, or in the case of our interferometer, the stretching and squeezing of the arms. So it's the relative displacement that a mirror experiences because of this, or two mirrors are, let's say, 4 kilometers apart, and then it's the relative stretching and squeezing of this distance. And that is what we try to measure. So there's this factor in front of it, 2 times the Newtonian gravitational constant, divided by c to the power 4th, the speed of light to the power 4th. And this gives this very, very tiny number. And indeed, ouch, because Einstein really thought we're never going to measure this. But this was before the invention of the laser and more precision stuff. So then there's this other factor, which is what we call the quadrupole moment, and then the second temporal derivative of that. And this is yeah, what a recipe of a strong gravitational wave should have. Accelerating masses close together, and that's what these black holes are. And then these 2 black holes are. And then it falls with 1 over the distance. Yeah, that's what that's the amplitude of the strain. So then on the right, you see if you now have a cylinder of coordinate points in 4-dimensional space-time, what does a gravitational wave then do? So it travels in this axis, and it only has an effect in the transversal direction. So if you have this ring there, then it's stretched and squeezed indeed. And so I can put these mirrors on this ring, and then these mirrors will do this stretching and squeezing that we saw before. So that's convenient because then we set up our interferometer and set up a kind of mousetrap. So if we make the arms of equal length, then no light is seen at the output port, at the photodiode. So once this gravitational wave passes by, the stretching and squeezing occurs, and because of the interference, some light because of the interference is then sent to the output port, and these flashes of light are the things that we actually see. So what did we see then the first time around? You see all these squibbles. These are the measurements of the stretching and squeezing of the arms in meters. And so we're really at a billionth of a meter here. And you see that over 0.2 seconds. So it's a really fast thing. We only saw the final stretch of the signal because we weren't sensitive enough at frequencies below 30 hertz in this case. So you see the noise of the detectors, and then out of that noise comes this signal that is explained by 2 black holes that come closer to each other. So the signal grows and they revolve around each other faster and faster. So also the frequency grows until they merge at this point here, and then the signal dies away. And that's what you see here. And if we calculate the expected signal given this source at a given distance, then you can see that the matching is quite remarkable, and it's expected via quite intricate calculations of general relativity. And so what happened outside science? So in the Big Bang Theory, you saw a t-shirt with these signals on there. Some people have decided that it was a great idea to put it on their arms, which is also fine. And this thing I actually bought, which is a mask which has the call sign of this first gravitational wave. So GW, gravitational wave, in the year 15, the 9th month on the 14th day. And then we continue. So that was the first two black holes that we saw revolving around each other, smashing into each other. So we've seen a couple of more after that, but at some point we also saw something else, which were two neutron stars flying around, crashing into each other. And this is interesting because two black holes crash into each other and they don't give off anything. They only give off gravitational waves, but not nuclear matter or baryonic matter or light or something like that. But when you smash two neutron stars together, then in the summer of 2017, we hit the jackpot, because here you see the same that I saw before, but in a different representation. So again, you see time, but now frequency, and the color means power. So the color becomes brighter, so the signal grows indeed, and the frequency grows indeed as well. So here you see this merger happening, and then 1.7 seconds later, this satellite called Fermi saw a gamma ray burst, and that was interesting, and people soon realized that those things were connected. And we said to our astronomer friends, like, go have a look in that patch of the sky. So that patch of the sky was determined by comparing the patches of the sky that our detector networks and Fermi and another satellite said it would be. So then you have here, you just have to look for 45 galaxies and find a new blip. So here there is a before image of that particular galaxy, and here an after image. And indeed, you see this new blip, and this new blip is called a kilonova. And a kilonova is a kind of radioactive oven in which all kinds of nice things happen, as we'll see in the next slide. But all astronomers, I think 70% of telescopes, electromagnetic wave telescopes around the world, started looking at this thing in the gamma rays, X-rays, UV, optical, the infrared, and radio. In a radio, it was even a very long, it lasted very long, the signal. So you see here the signal growing from August, in December, January, etc. So what is this radioactive oven? What is that all about? So you know the periodic table, but where do these elements come from? Well, from the Big Bang, we know hydrogen and most of helium come. And then the other stuff is made in stars with fusion, but that at some point stops as well. Their stars explode, you get a bit heavier, but then you really have to have merging neutron stars or dying low mass stars to make this. But this merging neutron stars, this was just theorized, was never measured. And this is exactly what we saw in the light coming off this kilonova. So yeah, if you want to see it a bit closer, you can see, for example, that 80 or 90% of the abundance of gold found in the universe comes actually from these merging neutron stars. So now look at all your jewelry or whatever golden stuff you have in your house, and know that it's probably coming from merging neutron stars. So now that's what we saw and what we did with it. So now let's build one with us, the TU Delft engineers. So here you see Delft, of course, the station, old church, new church. This is actually where I lived. And now we go on a trip to the TU Delft. These things should go away. Yes, at some point. Yes. Okay. And then in the meantime, you look here on the right, where you see again our simple interferometer with this interference, which is aligning of these waves, and then you see flashes of light. This is highly exaggerated because the wavelength that we use is a micron, and as you saw, the stretching and squeezing of these arms is a billionth of a billionth. So that's 12 orders of magnitude different, but okay, it's simple enough to see. So what do we have to deal with? What kind of noises? So we have to deal with seismic noise, because if we put this mirror on the Earth, you're never gonna see anything, because the Earth is moving with nanometers or hundreds of nanometers. In any case, way too much for the signals that we try to see. So you have to suspend them, and we'll have a look at that later, how that works. But what kind of people do we need? Physicists, people from 3ME, but also we need to know something about the ground that these seismic isolators stand on. And so now I will go through all these different noises, and you can see here on the left if you're needed or not. So here we go. So of course we need vacuum tubes and other stuff around it, buildings for this light to go unimpeded between the mirrors. We need the best lasers in the world in terms of frequency and power stabilization. Of course, electronic noise gives us troubles, because we have to extract these signals from photodiodes. We have to do that in the lowest noise possible way. Then we talk about beams of light as if they are, constant beams of light, but of course they're made out of particles, photons. And so we have kind of quantum noise that we have to deal with. One of those quantum noises is radiation pressure noise. And so now we've succeeded with this seismic attenuation to decouple the mirrors from the Earth's motion. But now we've bombarded with these quanta, and of course there's uncertainty in their arrival times, so that makes our mirrors shake again, typically at low frequency. So that's an issue. Another issue is that we operate at room temperature, and temperature, as you know, is you can think of temperature Brownian motion of the atoms. So it will make mirrors or the uncertainty of the where the mirror coating, so the front side of the mirror where the photons reflect off, where that actually is, because those atoms are moving by themselves as well. So we have to design for that. Then there's another quantum noise, which is called the shot noise, has to do with uncertainty in the arrival time of the photons at the photodetector. And then lastly, we have this signal. And of course, you can maybe convince yourself that that was a gravitational wave. But if you really want to know how far away is it, what kind of masses these objects have, what kind of spins did these black holes have, all kinds of interesting things that make you test general relativity if you are interested in fundamental physics, for example. And for that, we really need, for example, mathematicians and computer scientists. So, of course, I was going to give a presentation to you engineers, and I was going to show nice pictures of beautiful stuff. Because gravitational wave detectors, we've now looked at this simplified version, but of course they're more complicated. So if you start with the laser, then you have some kind of injection system where we have to clean the light for higher order modes. So we want a nice Gaussian beam, but imperfections in the mirrors or misalignments, they cause all kinds of weird shaped beams, and we don't want that. So we want that filtered out. Then they go into the interferometer where you have here the beam splitter, and then two very long, very high power cavities. And they make another cavities with power recycling mirror and signal recycling mirror. And what you need to understand about these cavities is that they are there just to make there be more power, probing the mirror surfaces, because more power means more photons, so it means less shot noise. And in the case of these long cavities here, you can think of an effective length, because now these photons bounce around, in the case of Virgo, then 400 times. So this 3 kilometers now effectively becomes something like 1,000 kilometers. So that's good for what you want to do. Then we start looking at seismic noise. So this is one of the things I work on. And I'll explain a little bit about this decoupling of the mirrors from the ground. So here's what we're up against, the ground. So what you see here is displacement, amplitude spectral density versus frequency. And this amplitude spectral density with this divided by square root of hertz is a bit of a funky unit, but just think of it as a spectral decomposition of a noisy signal. So if I have a noisy signal, it's made up out of all kinds of sinusoids, and these sinusoids at different frequencies get assigned a certain amplitude, and that's what you see here. So in most spectra, you see here this big bump at 200 millihertz. So that's once every 5 seconds. So where does that come from? It comes from the ocean waves bashing on the shore. So next time you go to the beach and you count to 5, you will probably see another wave, and that's a big issue for us because that's the largest contribution. Then there's a noise made by humans, and from 1 hertz onwards, and another. All these lines are typically, they're at a single frequency, so they're typically machinery around or something like that. So we saw this number already, 10 to the minus 18. So we have to do that from 10 hertz onwards. And we're here at 10 to the minus 9 or so. So we need a factor billion in attenuation. So how do we do that? We do that by using harmonic oscillators, or in the case of horizontal, we use a pendulum. So we suspend our mirrors via a pendulum. And if you later on want to test this out for yourself, you just roll out a yo-yo and you start moving it around. So if you move it around at low frequencies, you will see that this yo-yo just follows your hand, and you have a transfer or relative amplitude of 1. Then there's one frequency at which you can shake it up. That's the resonance frequency. But if you shake above that resonance frequency, so this is the kind of price we have to pay, then you see that we have this nice behavior of 1 over f squared. So that's a slope, but it's not nearly enough. So maybe you can hang a pendulum from a pendulum, then you can get to another slope. You have to have 2 modes, but okay. But it would also be nice to start that cutoff at lower frequency. So what can you do with a pendulum? So the frequency, this resonance frequency of a pendulum is 1 over 2 pi square root g over L. So g is fixed, pi is fixed. So the only thing you can tune is L. So if you want to go, for example, 10 times lower with your frequency, you need an L of 100 times more. So that's a problem because that's difficult and becomes unpractical quite quickly. So we can do this other thing called anti-spring technology. So we can just flip our pendulum, get an inverted pendulum. Of course, this is unstable. You know this because you've played around with a broom on your hand. And we put this angular spring at the bottom. So this is just a steel, not so thick, but just a steel little cylinder, for example. And then you see you have a lot more things to tune with, and you can tune this frequency to arbitrary low frequencies. So these transfer functions, they can be multiplied with this spectra that we saw before. So they're kind of low pass filter, if you will, and they will cut down the frequencies. And of course, we chain all these things. So the green one gets chained to maybe 7 stages of the blue one, etc. So you see that at Virgo, for example, you have inverted pendula. You see at Cagra, you start with inverted pendula because they're underground. You can just put another cavern up top, and then you start chaining filters, also vertical filters. You see here these blade springs. With LIGO, they do a bit differently. They work with more active platforms beforehand and then start suspending. But all these strategies are in need of sensitive inertial sensors. And there's one noise that I haven't talked about. It's called Newtonian noise. And this is that you've now have this mirror nicely suspended, but now there's a seismic wave passing, and this makes the local density, local mass distribution around the mirror change. And just by Newtonian attraction, it will make your mirror shake. So what can you do about that? You can put sensors on the ground, reconstruct what the effect might be, and then subtract it from the signal. And something else you can do, we will see on this slide. So here you'll see a detector sensitivity collection of all the noises we've talked about. So you can see the thermal and the quantum, and here you see this Newtonian noise. And so if we want to do better, what do we have to do? And especially, and that's a goal for Einstein Telescope, if we want to go below 10 hertz, because we want to know what is out there, let's say. So we can, you can read all the kinds of things that you can do. Typically for the thermal noise, of course, you can cool things down, go cryogenic. And for the Newtonian noise, you have this array of sensors, but the other point is we have to go on the ground. So you cannot take Virgo or LIGO and go on the ground, so we need a new infrastructure. So one of these new infrastructures is the Einstein Telescope. The other one is Cosmic Explorer. It's a kind of 40-kilometer LIGO on the surface, and that's what they're going to do in the US, it seems. But in Europe, we really want to go underground because we want to go into this below 10 hertz frequency regime. And so here for scale, you see LIGO. So it's going to be much bigger, all underground, and it's going to be built either in Sardinia or in Limburg. And that depends on seismic studies that are underway and politics. And it's actually quite interesting because yesterday there was a big meeting where three of our people, so three of our leaders, let's say, had to defend our proposal at the S3 kind of infrastructure that infrastructure roadmap. European infrastructure roadmap that we also will see later in the timeline. So now let's have a quick look. We start underground, so it's dark. So let's have a look how Einstein Telescope looks like. So here you see it, the logo of Einstein Telescope. If you map that logo underground, you can see here these 3 interferometers, actually 6 interferometers moving into each other. You see all these beams running through the vacuum tubes. Here, these suspension chains with underneath clean rooms where the mirrors are prepared. And these mirrors can then be hoisted into these large vacuum vessels where the suspension chains are. So you can just click it on, let's say, from the bottom. And there you see already a mirror that maybe these guys are replacing. So here we see more of those things, more clean rooms. It's going to be quite an operation indeed. Here you see a main cavern, very, very long towers indeed. And then we go to the surface again, see our gravitational waves, hope to catch them. And all of that is done underground and where nobody has to be bothered by it, let's say. So when will this thing be built? So the idea for Einstein Telescope is from 2005. And by the way, once you get these slides, all these things are clickable links. So you can have a look at these things and get more details about these figures, for example. But we made this conceptual design report in 2011. Then we did something else. We still had to measure actually the gravitational waves, so we were a bit distracted. But now we're really back on track to send this CDR as an updated proposal to this S3 as I talked about the roadmap. If we get onto this roadmap, then we can continue with site selection, which is done in 2024, and then hopefully constructed in 2028 until then and operated in 2035 and beyond for like 50 years or so. This is really an infrastructure for the future. And in the meantime, the Instrument Science Board, on which I am co-chair of the auxiliary optics suspension, so let's say the small towers, for the optical benches, for example, we want our technical design report ready in 2026. And so the difference between a CDR and a TDR is maybe, so for example, with the CDR, you say, we have a vacuum tube, and that's going to be fine. And with the TDR, you're really going to say it's going to be made out of this metal with this surface roughness, and that's going to cause us this scattering and those kinds of things. So moving on to, you saw that there's lots of new lasers, optics, cryogenics, caverns, lots of new technologies that we have to do. So yeah, we can think about that long and hard, but it would be nice to do prototypes. So one of these prototypes is actually built in the Netherlands. It's called ET Pathfinder. It's a 10-meter long interferometer, which is going to test lots of different technologies, so different temperatures, different laser wavelengths. Something that I'm working on from UC Louvain is the suspensions that go onto this detection bench. So there's going to be a bench here with all kinds of tinier optics, and those have to be suspended by themselves as well. So these suspensions you see here, for example, and it's going to be quite crowded. So we need to do our best in keeping these things nice and compact and fit into these structures. And an example of a benchtop suspension that you see now here of LIGO is in this picture. Then another prototype or sack of money that was given to a bunch of people, mostly Belgians in this case. It's called eTest, and it's part of it's subdivided into geological work and building a prototype. And the geological work is essentially an extensive survey of the area to really find a good location for this massive triangle. Because you think, I put it on the ground, no problem. But you have to do all kinds of studies because, there are wind turbines, factories, things that are maybe going to be built in the future, fault lines, hydrogeological stuff that you don't want. You really have to do a bit more than just knock on the floor and make sure it sounds good. And so then the other part of eTest is prototype suspension. This is going to be one suspension, so it's not going to be an interferometer. It's just showing that we can suspend a very, very heavy mirror made up of silicon. So silicon is the new material that we're going to do because of thermal noise, we want to cool down. But by cooling down, we can't use our present technology anymore, fused silica, because it becomes very, very lossy. So this figure goes down by 4 orders of magnitude, so that's unacceptable. So we have to use silicon. But the problem is silicon is not transparent anymore for 1 micron light. So we have to go to 1550 or 2 micron. And so we need a whole set of new technology. And so this can be a test bed for that, but also it can be a test bed for cooling techniques, suspension techniques, and more interesting for me, also sensor techniques. So these kinds of sensors are the things I like to build. And here you see a picture of the one I did for my PhD. So here you see a frame with therein suspended a proof mass. And so the frame will move with the stuff that you're trying to measure. And then by inertia, the proof mass will lag that motion a little bit. So if you then, so it will hang still, let's say, while the frame is moving along with the thing you're trying to measure. So if you then can determine the position of the proof mass with respect to the frame, then you're in business. Then you have your vibration sensor. So we use a readout. We really like interferometers. So here I built this little centimeter scale interferometer, and this sends a signal to this actuator to keep everything in check. So as I said, we are now going cryogenic. So I want to make, well, at least the first thing, make this thing out of niobium, because niobium becomes cryogenic, becomes superconducting at cryogenic temperatures. And then I can make everything a bit less lossy, especially in the actuator. So again, you see an interferometric readout, which will go towards these, which will send signals towards this actuator. But I also feel that this thing should only look at the tiny motions, and I take out the large motions using this Rasnik. And Rasnik is something that I worked on during my, well, I continue to work on, but I started working on that in my master thesis that I did at TUDelft. Yeah, so what are the kinds of sensitivities that I make? Again, you see displacement versus frequencies. And here you see, frequencies that are interesting for Einstein Telescope, 1 Hertz or below. And you see that with the thing that I was developing was not very good. It was at room temperature. Well, it was quite good, but not good enough for what I try to do now. And at room temperature, we can stretch it a little bit with a different actuator. But if we go cryogenic, then the thermal noise will go down and down and down. And then this line is something that I think we can achieve. And then the thermal noise hits your readout noise. And those are the 2 dominant noises that we have here. And so is that interesting for Einstein Telescope? So here you see again this collection of noises, our noise budget of the detector. And you see that, these are displacements that you're never going to reach, but you're also never going to put a sensor on the mirror itself. So you're going to put a sensor on the platform above the mirror, and and that one's also cold. So that's my plan. And then what I measure there, I project then down to my mirror motion. And I think that with these sensitivities that I reach here, that I can make an impact in monitoring for sure, because we have this, we have to cool them down, and cryogenics also always means vibrations. So, you know, look at your fridge, for example, it's always shaking a little bit. Same with our cryocoolers. And so we have to monitor that. And maybe I can also add to control. But with these sensitivities, also other people got interested, and I'm now part of this lunar gravitational wave antenna stuff. And on the next slide, I would like to show you two concepts. One is a kind of Einstein telescope in space. It's called LISA, and it's huge. So these arms are like 2 million kilometers. So if you put the sun inside here, it would fit. And that one is trailing on like 20 degrees or something, trailing the Earth orbit. And that's the idea. And then, you know, you have to shoot these beams over 2 million kilometers. So they are quite big when they arrive at the other satellite. But, you know, you have to catch them and somehow of those picowatts make something. Same concept, you know, stretching and squeezing of the arms, and then measure that. And then the other thing is a slightly different concept. It's the lunar gravitational wave antenna. So we put my or other sensors on the Earth, on the moon, and then a gravitational wave passes by the moon and stretches and squeezes the moon. And of course, the moon has certain normal modes. So for example, if you hit your table, you will hear a sound. But if you hit the moon somehow, you will also hear a sound, but really at 1 millihertz or something. So very, very low hum. And if that happens, then that little hum must be measurable by these sensors, and that's how we're trying to measure all that. So if you now compare all that, then you have these sensitivities again. You see ET here on the right. You see LISA here at much lower frequencies, really getting into the microhertz. And then this lunar thing is a kind of bridge where the two things don't have enough sensitivity. And that's what we're trying to do. And so concluding, a bit over time, sorry. Concluding, now that we've measured gravitational waves, you might think, okay, done. Why do you want to continue? But as with electromagnetic waves, that would be the same as saying to Galileo after he appeared through his, the first telescope that was, I think, made by a Dutchman. But and then say, well, we don't need to look at other wavelengths, or because, for example, without neutrino telescopes, we wouldn't understand the sun at the level that we understand it now. And you know, we're trying to build a sun on the Earth with nuclear fusion. So I think it's quite important. So and you know, if you want to be romantic about it, then it's kind of impossible to know, but really exciting to imagine what lurks into the rest of the gravitational wave spectrum. And then I would like to end with, this will all be sent to you, but in the lockdown, if you want to binge watch something other than Netflix, then you, of course, want all this gravitational wave material. And if you speak Dutch, you can even look at this Zwaartekrachtsgolven Klokhuis episode, where I was part of making it and have a couple of seconds of fame, etc. So thank you very much for your attention.